In this talk, I will briefly present my work titled Training Binarized Neural Network the Easy Way, which is a collaboration between myself, Alistair Powen, and Roger Pausel at Toshiba Research Cambridge. In this work, we introduce a novel method for training binarized neural networks, which we name BNEW. Binary neural networks, an extreme form of quantized neural network, where the majority of the parameters within the network are quantized to take binary values, specifically 1 or -1. There are two main types of network that get referred to as binary neural networks. The first, which I will refer to as binary weight networks, only quantize the weights of the network and leave the activations to retain floating point values. The second, which I refer to as binarized neural networks, have both binary weights and activations, and will form the focus of this talk. For both types of network, some select parameters retain floating point values, as binarizing all parameters typically leads to a very large drop in performance. The benefits of binary neural networks stem from the fact they can replace many of the expensive computations within neural networks with cheaper ones. In binary weight networks, dot products can be implemented using additions and subtractions, avoiding the need for expensive floating point multiplications. In binarized neural networks, dot products can be replaced with even cheaper and quicker bitwise operations. So why are binary neural networks useful? Both binary weight network and binarized neural networks require significantly less memory to store parameters than their floating point counterparts, as they only require a single bit parameter rather than the normal 32. Another result of the cheaper computations is faster inference speeds and less latency. Prior works estimate binarized neural networks can offer up to 50 times faster inference speeds on CPUs and approximately 5 times faster inference speeds on GPUs. However, the exact improvement is hardware and implementation dependent. Binarized neural networks also lower the computational and energy costs at inference time, and thus can be used on lightweight mobile hardware. Some applications binarized neural networks are particularly well suited for are those where minimal power consumption is important, such as remote sensing applications or in electric vehicles. We next give a very brief introduction to binary neural network architectures. Binary weight networks typically reuse conventional architectures designed for floating point operations without any modification. Binarized neural networks, on the other hand, require modification in order to ensure that activations are binary. However, typically they go far beyond this and present significant modifications. Much of the recent work on binarized neural networks has focused on developing architectures that are well suited for use with binary weights and activations. In general, these works suggest adding additional branches or a few real-valued scalars to help boost performance. In order to ensure the activations are binary within a binarized neural network, the sign function is used before each convolutional layer. However, the gradient of the sign function is the delta function and hence is 0 almost everywhere. Thus, in order to backpropagate through the sign function, its gradient must be approximated with a continuous alternative. The two most popular choices are the straight-through estimator, which approximates the gradient of the sign function with a clip function, and a triangular approximation to the delta function introduced by Liu et al. As part of their bi-real model. For the rest of the talk, I'll use the following notation. W superscript b will denote the vector parameters we want to take binary values. W superscript r will denote parameters we're happy retaining floating point values. And W with no superscript will represent all parameters within the network. For most binarized neural network, WR, the real value parameters, contain the parameters of the first layer, last layer, any batch neural parameters, biases, or the parameters within bottleneck layers. Hence, with this notation defined, the task of training a binarized neural network can be expressed in the normal empirical risk minimization setup with the additional constraint that WB must take binary values. However, this is now a highly nonlinear and non-convex mixed-input program and thus is NP-hard in general and does not permit an efficient solution. We will now introduce the most popular previous method for training binarized neural networks. What is now known as the straight-through estimator method was originally introduced by Kovacs et al. In 2015 to train binary weight networks. However, it was adopted by Huber et al. The following year to train binarized neural networks. This approach relies on introducing a set of auxiliary parameters, W tilde b, for each of the binary parameters, and these auxiliary parameters retain real values during training. We don't have time to go into all the details, but this method at a high level binarizes the auxiliary parameters before each forward pass to produce WB, a binary model. The gradient is then evaluated on this binary model. However, the resulting descent step is then applied to the auxiliary parameters, W tilde b. Thus, the auxiliary parameters allow the gradients to be accumulated and produce a sign change over multiple iterations. At the end of the training, the auxiliary parameters are no longer needed and can be discarded. This method is still popular for training binary neural networks, however it does not have a strong theoretical justification. Many methods have been based off the straight-through estimator method with different degrees of success. However, these all rely on some form of auxiliary parameter during training. Unlike most existing methods for optimizing binarized neural networks, we do not use auxiliary parameters. We instead relax the constraint on WB to its convex hull and introduce a regularization function R that penalizes non-binary solutions. This regularization term strength is determined by a hyperparameter lambda. You can see when lambda is significantly large, we are guaranteed solutions with binary parameters. A very similar approach was shown to be effective by Bai et al. In 2019 for training small binary weight models, which they named ProxQuant. In their work, they introduced two regularization functions that penalize different norms of the distance between WB and its binarized value. These W-shaped regularizers are then used to define proximal operators that are applied after each descent step, slowly encouraging the model to become binary. Our method, BNew, has a lot of similarity with the approach of Bai et al. Indeed, their work was the inspiration of ours. However, our work differs in three important ways. First, and most significantly, we show this technique can be used to train highly accurate neural networks with both binary activations and binary weights, whereas Bai et al. Only considered binary weight networks. When using this sort of continuation method to train a model with both binary weights and activations, it is not obvious if one should binarize the weights and activations simultaneously or sequentially. We show a sequential approach, binarizing the activations first, is effective. Second, the work of Bai et al. Only present results for small networks trained on relatively small data sets. There is no indication in their work if this method scales to larger data sets with more realistic image sizes. We demonstrate this is true. Lastly, we present a small number of other improvements, such as an improved regularization function, which can be thought of as a negative weight decay. At each step, BNew selects the next iteration as the minimizer to the following minimization. This results in a modified projected gradient descent step. However, in practice, we use an Adam-like descent step within this update as we find it produces better results. In order to train a binarized neural network using BNew, we use the following training procedure. First, a model with binary activations and real-valued weights is found by using the update with lambda t set to 0. Second, we slowly encourage WB to take binary values by linearly increasing lambda t throughout training. Before the end of training, WB is hard quantized to take binary values, and then we fine-tune the real-valued parameters to these final values. BNew enjoys the same worst-case convergence rate as ProxQuant when applied to smooth and non-convex problems. We investigate the performance of networks trained with a number of different optimizers for binary neural networks on the CIFAR datasets, with and without distillation. For the specific details of these experiments, please refer to the main paper. However, the main takeaway from these experiments is BNew performs equivalently with the best existing methods. We also present results for larger networks trained on the ImageNet dataset, and whilst our result is not significantly higher than the previous state-of-the-art ReactNet, it shows that this method does indeed scale to large binarized neural networks, and our results are very competitive. Additionally, in the supplementary material of the paper, we provide an ablation study investigating the effect of different aspects of the network architecture and training procedure. BNew has two minor disadvantages. First is sensitive So the hyperparameter beta controlling the rate at which the regularization strength is increased, and its optimal value depends on the total training time. Second, intermediate models during training do not give a good indication of final accuracy, and thus full training runs are required. In this talk, I have introduced BNEW, an extremely simple method for training binarized neural network that does not use auxiliary parameters. BNEW can easily be applied to any architecture without modification and produces strong empirical results in our experiments. Additionally, with some mild assumptions, BNEW offers provable convergence rate, which again sets itself apart from other binary network optimizers. Thanks for watching this talk, and please get in touch if you have any questions after reading the full paper.